NOAA's ocean monitoring network just logged the highest ocean heat content ever recorded. Not a seasonal blip, not a single hot summer in one bay. The whole global ocean, measured from the surface down to 2,000 meters, is holding more heat energy than at any point since instruments started tracking it. And here's the part almost nobody is talking about. The record number itself isn't the scary part of this story. What's underneath it is. If you live near a coast, if you've ever booked a beach vacation, if you eat seafood, or if your home insurance bill has quietly doubled in the last few years, the next 20 minutes explains why, using nothing but numbers, you can check yourself. By the end of this video, you'll know exactly what ocean heat content actually measures and why it's a better warning sign than air temperature. You'll know the specific number NOAA and Copernicus just confirmed and what a fraction of a degree in ocean water actually does when it's spread across an area that size. You'll know why this year's El Niño is being supercharged by that stored heat and what that means for storms and rainfall patterns over the next several months. And you'll know which places and which people are first in line to feel it, plus what you can actually do about it starting today. No fear-mongering, no vague warnings, just the data trail laid out in order. Before we get into the mechanism, here's the one thing. Worth doing right now if this is new to you. Subscribe if you want to see how this number moves over the rest of the year, because ocean heat content doesn't spike and vanish like a heat wave does. It builds slowly and it unwinds slowly, which means this isn't a one-time headline, it's a trend you can actually watch develop in real time. And here's a question worth sitting with rather than just answering in the comments. Has your local coastline, your local fishing spot, or your local reef changed in the last 5 years in a way you noticed before you ever saw a headline about it? Because a lot of the people who live closest to the ocean noticed this shift before any agency put a number on it. So what does ocean heat content actually mean, and why measure that instead of just checking the temperature at the beach? Think about a bathtub. If you dip your hand in at the surface, the water might feel warm, but that tells you almost nothing about how much total heat is sitting in the tub, because most of that heat could be sitting deeper down, out of reach of your fingers. Ocean heat content is the equivalent of measuring the whole tub, not just the top inch. Scientists do this with a fleet of more than 3,000 robotic instruments called Argo floats, drifting all over the world's oceans. Every 10 days or so, each float sinks down, records the temperature and salinity as it goes, then rises back to the surface and beams that data up to a satellite before sinking again to repeat the cycle. Combine that with shipboard instruments, satellite measurements of sea surface height, and older tools like expendable probes dropped from research vessels, and you get a genuinely global picture of how much extra heat energy the ocean is storing, not just how warm the surface feels on a given day. Here's why that distinction matters so much. The ocean is enormous, and water is very good at soaking up heat without its temperature changing much. That's the same physical property that makes a thermos work, or why a swimming pool stays cool longer into the evening than the pavement around it. Because the ocean covers most of the planet and holds heat so efficiently, it has absorbed the overwhelming majority of the extra heat energy trapped by rising greenhouse gases since industrialization began. Think of the atmosphere as a blanket that's gotten thicker over the decades, trapping more of the sun's energy near the surface instead of letting it radiate back out to space. Almost all of that trapped extra energy doesn't stay in the air. It gets absorbed by the ocean, like a sponge sitting under a slow drip, soaking up far more than a first glance would suggest. That's why ocean heat content is often described by scientists as the real ledger of how much the planet is warming, more reliable than air temperature alone, because air temperature bounces around year to year with weather patterns, while the ocean's heat storage moves in a much steadier, harder-to-fake trend line. There's a second reason this measurement matters more than a simple thermometer reading at the beach: depth. Heat doesn't just sit at the surface. It gets mixed downward by waves, currents, and storms, the same way stirring a pot moves heat from the bottom to the top and back again. Most of the heat scientists track is measured from the surface down to 2,000 meters, roughly the height of 5.5 Empire State Buildings stacked on top of each other, submerged. The bulk of the recent heat gain is concentrated in the upper 700 meters, the layer closest to the surface, which also happens to be the layer that interacts most directly with the atmosphere, with hurricanes, and with the fish and coral that people depend on. Deeper water warms more slowly, but once it does warm, it holds on to that heat for an extremely long time, which is part of why this measurement behaves less like a light switch and more like a bathtub that's slowly, steadily filling up, one small trickle at a time, long after anyone standing nearby has stopped noticing the tap is even running. Now for the actual numbers and what they mean once you translate them out of scientist speak. NOAA's long-term tracking, using data going back to 1993, shows the global ocean has been gaining heat at a rate of roughly 0.66 to 0.74 watts per square meter, averaged across the entire surface of the Earth. That number sounds tiny and abstract, So here's the translation. Imagine covering every square meter of the planet's surface, land and ocean combined, with a small nightlight bulb running continuously, day and night, all year. That's roughly the scale of extra energy being absorbed nonstop across the whole planet for over 3 decades running. It doesn't sound dramatic in a single sentence, but multiplied across the entire surface of Earth and sustained for 30 years, it adds up to an amount of stored energy that's difficult to put into everyday terms. Physicists have compared similar totals to the energy release of several atomic bombs detonating every single second, just to give a sense of scale, not because anything is exploding, but because that's the only way to make a number this large feel real. On top of that long-term trend, this year brought a sharper spike. In June, surface temperatures hit a record high for that time of year, 21 degrees Celsius, according to Copernicus Marine Service data, beating the previous records set in 2023 and 2024. 2 degrees Celsius might sound small if you're picturing your own body temperature, but ocean water doesn't warm the way air does. A shift like that, sustained across an area the size of entire ocean basins, represents an enormous quantity of the additional stored energy, and it's the kind of shift marine biologists watch closely, because it's exactly the trigger point where coral and other temperature-sensitive marine life start to struggle. Speaking of coral, here's a number that translates heat content into something you can actually picture. NOAA's coral reef. Watch program confirmed the world has just come through its 4th global mass bleaching event, and it hit an estimated 84% of the world's reefs across all 3 major ocean basins between 2023 and mid-2025. 84%. Picture a coral reef as a city built by the coral animals themselves, providing the housing, the food source, and the nursery for roughly a quarter of all known marine species. When water gets too warm for too long, the coral expels the colorful algae living inside its tissue. The same algae that provides both its color and a big share of its food, and the coral turns bone white. That's bleaching. It doesn't always mean the coral is dead yet, but it means it's starving and stressed, and if the heat doesn't ease up in time, it dies. Recovery, when it happens at all, isn't quick. A bleached reef that does bounce back typically needs somewhere in the range of a decade of stable, cooler conditions to regrow the coral tissue and reestablish the algae partnership it depends on, which is exactly why a pattern of bleaching events landing closer and closer together, rather than once every decade or two, is treated as such a serious warning sign by the scientists who track it. A reef that's hit again before it's had time to recover doesn't just stay damaged. It can lose ground it never gets back. A study published in the journal Coral Reefs found that the heat stress driving this has run essentially unbroken from 2018 through 2025, and warned that bleaching, which used to be a rare once-in-a-generation event, is becoming close to an annual occurrence for many reefs. Then there's the El Niño angle, which is where this stored ocean heat stops being an abstract long-term trend and starts actively shaping the weather over the coming months. El Niño is a natural climate pattern where the tropical Pacific Ocean warms up more than usual, and that warmth changes wind patterns and rainfall distribution across huge parts of the planet. Think of it like a thermostat setting for global weather that flips every few years. In June, NOAA officially declared an El Niño was underway and put the odds of it becoming a very strong one, meaning tropical Pacific temperatures more than 2 degrees Celsius above the long-term average at its peak between November and January, at 63%. If that plays out, it would rank among the strongest El Niño events since reliable records began in 1950. The World Meteorological Organization has said the pattern is strengthening quickly and has already warned it raises the odds of drought in some regions, unusually heavy rain in others, and more frequent or intense heat waves worldwide. The reason this matters for our topic is that El Niño doesn't create heat out of nothing. It's essentially a mechanism for releasing some of that built-up ocean heat back toward the surface and into the atmosphere, which is part of why a hot ocean and a strong El Niño tend to arrive together and reinforce each other. Here's the mechanism in slightly more detail, because it's genuinely useful to understand rather than just take on faith. Under normal conditions, trade winds blow steadily from east to west across the tropical Pacific, piling up warm surface water near Asia and Australia, while allowing cooler, nutrient-rich water to rise up from the depths off the coast of South America. During an El Niño, those trade winds weaken, sometimes even reverse for stretches of time, and that warm pool of water that's normally pushed to the west sloshes back eastward across the Pacific, like tilting a bathtub and watching the water at one end slide toward the other. That eastward sliding warm water then sits closer to the surface across a much larger stretch of ocean, where it's far more available to transfer heat and moisture into the atmosphere above it, which is exactly the fuel source that reshapes rainfall and storm patterns across entire continents, sometimes on the opposite side of the planet from where the warm water actually is. That's why a research station in the tropical Pacific can produce a number that ends up shaping drought forecasts in southern Africa, or rainfall outlooks in the southern United States months later. The ocean and the atmosphere aren't separate systems reacting to each other from a distance. Over a timescale of months, they behave almost like one connected system, trading heat and moisture back and forth continuously. To understand how unusual this is, it helps to look backward. Ocean heat content records go back to the 1950s in a rougher form and get much more precise, starting in 1993 with the launch of dedicated satellite and float-based monitoring. For most of that record,